For years, the aerospace industry has been dealing with a complex, serious, and delicate problem, a real Achilles heel, which prevents rockets from being able to put payloads into space without scientists and engineers having to solve a series of complex calculations to determine how much fuel is needed for our rocket to carry that payload into space in the most efficient and economical way possible. This problem is known as the rocket equation, a series of calculations that has always been behind every launch. Any mistake in these calculations and the rocket will end up lifting off with more fuel than necessary, which will be more expensive, or it won't reach orbit due to lack of fuel. But a company plans to change this situation. That company is SpinLaunch, which intends to launch satellites using a vacuum centrifuge, an arm made of high-strength carbon fiber, which will hold the satellite at one end, and at the other, a counterweight to keep the structure balanced. It will spin for about an hour, reaching around 450 revolutions per minute, and a force of 10,000 Gs or 10,000 times the force of gravity. Then the satellite will be launched at 8,000 kilometers per hour towards space. After passing through the dense layers of the atmosphere, the projectile will open up, revealing a small stage that will propel the satellite into its orbit. The idea is quite innovative and promises to cut costs by up to tenfold, making it possible to carry out up to 10 launches per day. These are unimaginable numbers with current rockets, even when using reusable rockets like SpaceX's Falcon 9, which need about 21 days between launches when using the same rocket. Currently, SpinLaunch carries out its launches using a scaled-down model, just over 50 meters tall, called the A33 Mass Accelerometer, located at Spaceport America in New Mexico, with the entire system powered by electricity. But here's how this system will actually work. The A33 is a 34-meter diameter suborbital accelerator used for testing. Basically, it's a huge chamber that has the air inside it removed, thus creating a vacuum. In the final version, with a 45-meter radius for orbital flights, there will be a huge rotating arm made of high-strength carbon fiber in the middle. This arm is powered by 2 electric motors. A company-developed projectile will be attached to the tip of this arm. Inside, it will contain the payload that will be launched, in this case, a small satellite, as well as 2 rocket stages for the final boost to orbit. This projectile is mostly made of carbon fiber, plus some aluminum and copper at the tip. None of those materials are very resistant to high temperatures. We'll soon understand why these materials were chosen. This projectile will be attached to the spinning arm by a mechanism developed by SpinLaunch, which is kept secret. It's probably an improved version of the current mechanism. Let's go to our test airfield. So this arm will spin for about an hour until the projectile at the tip reaches a linear speed of 8,000 kilometers per hour at about 450 revolutions per minute. After reaching that speed, an extremely precise mechanism will release the projectile towards the exit tube, which will also be at the same vacuum level as the rest of the chamber. From there, the projectile continues into space. With this concept, Spin aims to reduce the current problems that companies in the aerospace sector face when trying to put payloads into space, such as rocket fuels, all the necessary equipment and systems, the complex rockets, and the huge number of personnel from different countries, areas and expertise required, the infrastructure, among others. And all of this for just one launch. Recently, they carried out the 8th successful test with a reusable projectile, although the projectile still excels a lot during ascent. Although the idea is good, the whole concept comes with many problems and challenges that must be overcome. One of the first is how to create a vacuum in such a large structure. Creating a perfect vacuum in such large structures is extremely expensive and involves precision engineering. But fortunately, SpinLaunch doesn't need a perfect vacuum. They just need a certain level of vacuum, enough to reduce drag during the spin at the extremely high speeds of the rotating arm, and also to prevent overheating both of the projectile at the tip and of the arm itself at those speeds. and also to reduce possible oscillations in the entire structure caused by slight imbalances between the projectile and the counterweight. The other problem, and the one that intrigues the most but apparently has already been solved, is the extreme precision required to release the projectile at the exact moment. The release mechanism needs to work extremely precisely to release the projectile at the exact moment, so that it is on the correct trajectory toward the launch tube. All of this already takes into account the slight air resistance inside the chamber, the timing, among other factors. It's something extremely complex and precise, and it requires high-precision engineering. Since small delays in the signal sent, in the computer that processes and controls, the release mechanism itself, among others, will make the projectile crash into the chamber walls instead of heading for the launch tube, which would be a terrible disaster. It will also be necessary to find an equivalent counterweight for each payload that will be launched, and solid or liquid counterweights can be used. In addition, after the projectile is released, the counterweight also needs to be released so as not to unbalance the whole system. But where the counterweight goes has not yet been disclosed by the company. Another problem is the set of two doors that must open to let the projectile pass and then immediately close to prevent outside air from pressurizing the inside of the chamber, which will contain a vacuum, thus preventing damage to the system that will still be spinning. This set of two doors, which must open and close, has to operate much, much faster than the blink of an eye. In this video from Real Engineering, you can see a prototype of these doors in full operation. The door closes in approximately 30 milliseconds, about the same time it takes for an airbag to inflate during an accident. But one of the big disadvantages of this whole system is the inability to launch much heavier payloads due to limitations in the system's own operating dynamics. So larger payloads, both in weight and volume, will still be launched by regular rockets. The amount of energy required to accelerate payloads to 8,000 km/h is also quite significant, but it's still cheaper compared to filling rocket tanks with millions of liters of propellant at cryogenic temperatures. As a long-term goal, Spin Launch aims to carry out up to 10 launches per day, but for now, their goal is to perform up to 5 launches daily. With the final system fully tilted at 35 degrees and capable of launching satellites of up to 200 kg, currently the launches made with the A33 reach 1,900 km/h and an altitude of 9.3 km. Oh, and remember the tip of the projectile, made of aluminum and copper, which aren't materials very resistant to high temperatures? Well, they chose these metals because, among other things, they are lightweight metals that won't increase the weight of the projectile too much. And also because, due to the high speed at which the projectile is launched, it can pass through the various dense layers of the atmosphere quickly enough, not giving much time for the projectile to overheat to the melting point of these metals. But certainly the biggest problem is how satellites, which are ultra-sensitive and delicate equipment and often contain liquids inside, will withstand the tremendous spinning forces at more than 10,000 times the force of gravity. According to the company, they are developing a new class of ultra-low-cost satellites for high G-force environments. According to the company, they have managed to prove that the current materials and processes used to build satellites, as well as all the electronics, can be used to build satellites for high G-force environments without increasing costs much at all. Something they discovered was that common everyday equipment, such as some cameras, cell phones, integrated circuit boards, batteries, computers, microcontrollers, processors, among others, already withstand forces of 10,000 G without needing any modifications, which is very good. In addition, the structures, mechanical parts, batteries, propulsion systems, and solar panels developed by the company for such environments also do not have a significantly increased cost or mass. Which means that companies also don't need to worry about the cost or mass of these other components, specially adapted to high G-forces. All these findings make the spin launch concept very promising and greatly increase the chances of it being the next company to revolutionize the aerospace sector, with the first launches scheduled for 2025.
5,